Okay. Okay, so welcome everyone to today's PhD seminar. I'm excited to be presenting Yuga Iguchi today. His supervisors are Alexandros Beskos and Matthew Graham, and he'll be talking about parameter estimation with increased precision for elliptic and hypo-elliptic diffusions. So without further ado, take it away, and I'll just leave you with the commands here. Okay, so you should be able to just control it with the arrows as usual.
So thank you very much for organizing this lesson, and thank you for coming here for the great Halloween evening and great space. I'm really surprised because this is quite nice space, feeling like being some lecturer, right? And let's focus about the joint work, the parameter estimation for the diffusion processes. And this is a joint work with my supervisor, Alexandros, and Matt Graham. He's from the Advanced Research Computing Center. And my second supervisor is Sam Livingstone. So, yes, so this talk is about the parameter estimation for the stochastic differential equations from discretely sampled observations. So for instance, that is the stock price in time series, or maybe the position of the particle in context of physics. And I would like to say that this is challenging and important. The first thing, this is because the solution of the, in general, that multidimensional SDE does not admit the post-form transition density. And also, we cannot exactly simulate this process. And secondly, the SDEs appear in so many applications, such as finance and physics. So let's see the model. The model is given in the general form like this: the d-dimensional SDE. The XD is actually the d-dimensional vector, and you will see this theta. That is the parameter we want to estimate from the observations. And the coefficient Vj, this has the RD dimension. So the right-hand side is also the D dimension. And then the B, this is the Brownian motion, which determines this system as a stochastic. So this D-dimensional Brownian motion gives some randomness in this system. So this is the SDE in general form, and this research focuses on basically two types of SDEs. The first type is specified as the diffusion matrix B. This is the D times DR matrix. We assume that this diffusion matrix has full rank. So this is a first type SDE, and actually quite common assumption in applications. And secondly, we also consider the case that the GUI does not have full rank. And actually, this type of model appears in application. You can find so many examples in application, in fact. So in order to treat these two types of SDEs, I would introduce the specific structure of SDE. In particular, this SDE can be split into two parts. That is the XR and XS. The XR, let's say that component is definitely driven by the Brownian motion, like that. And we have also have a smooth component denoted by XS. You will see that the XS is not directly driven by the Brownian motion and has only this drift of B and 0. So this is the specific structure. And we assume that XR has a DR dimension and the XS has the DS dimension. and ds might be 0 or not. And the theta is the parameter we want to estimate. And in the case of ds is 0, the system is belonging to the first type of SDEs, which means that the diffusion matrix has a full rank. However, if we assume that ds is not 0, the diffusion matrix does not have full rank. And especially for the ds is not 0, we assume that some kind of mathematical conditions called the Hellman's condition. And then the law of XT admits a logarithmic density. So roughly speaking, this tells us that even though the slope component is not directly driven by the Planck motion, but this Vs0 strongly depends on the left component XR, then this stochasticity of XR propagates into the axis. And then, even though the axis is not directly driven by the Planck motion, as a whole system, this system is stochastic. So the Hellman's condition roughly tells us that kind of information. And under this situation, the solution process is referred to as the hypo-elliptic diffusions. So this is a setting. And I would like to emphasize that. So actually, the statistical inference for the diffusion processes are quite classical problems. But for the hypo-elliptic diffusions, the theoretical analytical results are recently established, actually. So please see these two main contributions quite recently. And I would like to briefly share the ideas of those early literature. So we consider basically the degenerate, the hypo-elliptic diffusions. And they introduce a low-time Gaussian approximation for the intractable solution of SDE. So as I said, basically we don't know the exact form of the solution of X. So, and this is the XR at time delta. The delta is now simply by those quite smaller time. And in the right-hand side, this is expressed as the initial value plus the diamonds from the time 0 to time delta. And that is represented as the time integral and integral in respect to the graph function. However, the point is we cannot treat as a graphical constant like these integrals. So when the delta is small, we try to approximate the right-hand side with the Euler-Malin scheme. The Euler-Malin scheme means we simply put the initial value x into the xt inside the integral. So we get this type of approximation here. And the point is now we can exactly compute these quantities. This is the Brownian motion, and it is known that to follow the Gaussian distribution. So we can exactly simulate and compute this right-hand side. So we use this right-hand side as an approximation scheme. Let's say the local Gaussian approximation for the left component. And so let's see the smooth component. If we apply the same thing to the smooth component, we have a problem. We have a trouble. This is because this is not driven by Brownian motion. So there is no stochasticity if you apply the same approximation. So in their work, they consider the higher order stochastic Taylor expansion applying to the VS0. So they obtained additional higher order powers like this. And this quantity is known to follow Gaussian distribution. So now we get the stochastic system for the joint, for the whole points of x on the axis. And additionally, I mentioned the Helmholtz condition. And now that condition guarantees that this local Gaussian approximation has a Gaussian density with the positively definite covariance values. So the point is the density of the local Gaussian scheme is now intractable, and we can use it as an approximate likelihood for the intractable likelihood of the original xt. Then, using this approximate likelihood, we construct the maximum likelihood estimator, and then they show the statistical properties such as consistency and asymptotic normality. So this is the early works. So let's move to the contribution of this work. So in the early literature, in order to approximate the intractable transition dynamics of xt, they introduced some Gaussian approximation for the original intractable dynamics. But in this work, we propose the tractable advanced tools, which has a better accuracy in the sense of distribution. The first tool is the sampling scheme. This is used for the simulation of the diffusion process. And this sampling scheme itself is useful in the context of computational MCMC, so for example, only the sampling or simulation of the diffusion process is needed to do some basic inference. And in the second case, the second tool is the transition-based density scheme. So this is a closed-form transition density. So if we construct this type of density scheme, then we can directly use it as an approximate likelihood. And also we can define the maximum likelihood estimator. So the point is, these advanced tools are no longer Gaussian. So that is the point, but has a better accuracy compared with the locally Gaussian scheme. And finally, we show the benefits of using these schemes in the context of parameter estimation. So this is the outline of this talk. So, okay, this is the introduction. So let's see the advanced tools. Firstly, we will see the sampling scheme. I would try to provide the background idea to obtain this sampling scheme. So just, we apply the higher order stochastic dynamics.
Yeah, sorry, since we're passing on to another section, I just want to check that the people online can hear.
Okay.
Microphone is near the computer, and I don't know if they can hear you when you're there. When Yuga moves to the left of the screen, can you guys still hear? Audio is rather cracky. Okay. If the speaker is standing here like I am, is the audio better? Okay, so unfortunately, you're going to have to stay here because the microphone is here. Sorry about that. Okay, and then. Okay, thank you.
So let's see the sampling scheme. So the sampling scheme is obtained from the higher order stochastic data expansion. So the left-hand side is our target dynamics of X. And as we have seen before, that this quantity is approximated by the local Gaussian scheme, the X tilde. But now we add the higher order expansion terms like this. So the B hat is the differential operator acting on the original coefficients. And you will see the additional double and triple integral depending on the ground motion. And then we will try to use this as the approximation scheme, but we cannot use these quantities because, in fact, we don't know the exact distribution for instance, the double integral for the Brownian motion. So we replace those intractable distributions with the tractable random variables. And those random variables are given by the products of Brownian motion, or maybe including the time delta. And they are determined by a classical moment matching technique. And then, so we can now define the X bar as a sampling scheme, which has a better accuracy than local Gaussian scheme. So let's see in what sense does the proposed scheme is better compared with local Gaussian scheme. And the first property is that, yes, the X bar is explicitly computable by simulating the Brownian motion. And that is the first important point. And secondly, the scheme achieves the local weak third order convergence. That means for some test functions phi, so the difference between the target expectation, the left-hand side, the E of phi of X minus E of phi of sampling scheme, this difference is bounded by some constant times delta powered by 3. Now delta is assumed to be the small quantity. And so this means that a local weak third order convergence. And I would like to remark that in the case of a local Gaussian scheme, it achieves the local weak second order convergence. So in that sense, so if we consider the quite small quantity of delta, then if our sampling scheme has a much more accurate in the sense of the distribution. So this is the first property for the sampling scheme. So let's go to the transition density approximation. So the aim here is that we have in the left-hand side, we have the two intractable density. There exists a density, but we don't know the exact version of the left-hand side. So we try to approximate this quantity in the right-hand side. The X bar is the sampling scheme. So I will explain that. So the transition density means the X from the point X to the point Y with the step size delta. This is the transition density. And for this quantity, we need to approximate this quantity, and we try to derive a closed form small time expansion, making use of some probabilistic tool from Bayesian calculus. And then we truncate the expansion of the transition density scheme and define a tractable approximation P bar satisfying that this inequalities. Again, this P bar has the same role as the local weak third order approximation, as we have seen before in the case of sampling scheme. So this is the rough sketch of the transition density approximation. And then we obtain the transition density scheme in the form of right-hand side that is given in the density of locally Gaussian scheme times 1 plus some additional information. This phi is given like this, phi 1, phi 2, phi 3 with some time scale in front of those. And each phi function is analytically available. And this phi k involves the derivatives of SDE coefficients and also the derivatives of the locally Gaussian scheme that is determined as an elevated polynomial. So yes, these quantities can be exactly computable. And the second remark is that this expansion is actually novel in the hypo-elliptic case. Actually, in literature, there are several expansion formula in the case of elliptic. However, in the case of hypo-elliptic, this is, I think, the first attempt in the literature. So this is a transition density scheme. I will present some example of phi function later with the examples. So let's see the analytic results for the statistical inference. So far we have seen the two tools. The first one is a sampling scheme, and the second one is a transition density scheme. And we try to consider use of these schemes in the context of statistical inference, and then see the benefits of use of these schemes in the context of statistical inference. So we basically consider the two observations regime. The first one is a high frequency observations regime. The data set is given by xtk. The tk is the time instance. So we have the n discrete time observations, and we assume that each observation time interval between observations are equidistant. We assume they're equidistant. And for such a data set, we define the maximum likelihood estimator like this. And this L is the approximate likelihood given by the right-hand side. The point is, this approximate likelihood is given by, firstly, the log likelihood of local Gaussian part. Okay, so this is actually the log likelihood of Gaussian density. So this is normal, and this is actually used in the early literature. But now we add the additional term as a fraction term to remove the bias of the approximation. And we especially use the phi2 function as a fraction term. Phi2 is, please recall that the phi2 is obtained in the transition density approximation. And so now let's recall that this system again. So the beta is included in the drift term in the left component, and sigma is a diffusion parameter, and gamma is the drift parameter in the smooth component. Recalling this system, I will present the first main result. This is the asymptotic normality of the obtained maximum likelihood estimator. So under this asymptotics, which means the n is the number of data, and delta n is the observation time steps. We assume that this observation time step goes to 0, and also n times delta n, that is the time interval, entire time interval goes to infinity. With this step size condition of delta n, then we obtain the asymptotic normality, which means the left-hand side, the distribution of this left-hand side converges in the distribution of the normal distribution with some precision matrix I. So let's see this result, and let's consider what this result tells us. So maybe you will find that in front of the sigma, the beta gamma sigma star is the true value of the parameter. And you will see that, for instance, in the third, the sigma, you will find the square root n in front of the sigma n hat minus sigma star. This root n implies the convergence rate of the convergence rate of the COT, which means the variance of this the variance of normal distribution quickly goes to 0 with the rate of 1 over square root n, which means if we prepared so many number data, then we can basically succeed to estimate the true parameter in zero with the rate of 1 over square root n. So the same thing happens for the beta and gamma. So this result is useful in the sense that this gives the convergence rate of the maximum likelihood estimator. But this CLT only holds with the step size condition of this delta n. And this is quite important. And here I would like to add some important remark. That is, if we remove the fraction term from the approximate likelihood, then the above CLT, the same thing holds with a stronger condition on the step size, with delta n is the little order of n to the minus half. Actually, this is stronger than the red step size condition. So, which means this. So this is the advantage using the fraction term. So if we add the fraction term, we can get the under the weaker condition of the step size, we can get this CLT. So yeah, the proposing this kind of maximum likelihood estimator gives some flexibility over the statistical inference, even if we cannot get the quite so many number of data with the quite small step size. In the latter case, you need a quite small step size to obtain this type of CLT. However, this step size condition can be weaker in our new result using this fraction term. So this is the result in the high frequency observations received. And secondly, we will see the low frequency observations received. That is, now we assume the delta n is not small enough. And for instance, fixed with some value with some 1. And in that context, we will do, the data augmentation, which means we introduce. So now we have observations, but there's a large gap between the two observations. So in that case, the statistician introduced the M subintervals to impute the intermediate values in order to remove the bias. So in mathematically, I will explain that. So we have always in my mind that there exists some transition density, but now this delta n is not small. And this left-hand side is approximated by introducing the m-1 intermediate points. That is kind of the simulation by the user. So the right-hand side is the convolution of the, for instance, the sampling scheme or transition density scheme. So now the P bar H is the delta n over m. M is the number of imputation specified by the user. And this P bar H, the H is the inner step size. And then H is quite determined as a quite small quantity. And so this right-hand side approximates the left-hand side with the small bias. And what we did is that quantify this bias of the data augmentation. But in this case, we consider the elliptic case only. So under some conditions, we have the approximation, the bias of the data augmentation is bounded by some constant over m squared. M is again the number of imputation specified by the user. And the point is, this bias is 1 over n if we use the Euler-Martin scheme. But if we use the sampling scheme or transition, the developed transition density scheme, then this bias is 1 over n squared, which means that effectively the bias is reduced by using the new developed schemes. So this is what happens in the low frequency observations we're seeing and the analytic results. So let's see the numerical results. So firstly, we consider the high frequency observations we see. So we consider 6-dimensional SDE. This is a hypo-elliptic diffusion. The 3-dimensional rough component and 3-dimensional smooth component. And so I will skip the details of the model, but yes, this is actually the hypo-elliptic diffusions. And we try to estimate the parameters, 3 parameters, C, mu, sigma 2, by following the similar experiments from the early literature. And in this experiment, we would like to compute our new contrast estimator using the fraction term. And in this case, the fraction term is given like this. So this includes some h. This is the L-mid polynomial. And these L-mid polynomials determined as the partial derivatives of the log of Gaussian density. Yeah, I would like to emphasize here that the Python function is exactly computable. So let's see the numerical result. So here, what we did is that we generate the 50 path from simulation, and then construct the maximum likelihood estimator based on the observations. Then we computed the mean of the 50 replicates of parameter estimates and compare the 2 cases. The first one is simply use the locally Gaussian likelihood, and the second one is the locally Gaussian contrast with correction term. And you will see that in the estimation of the drift parameter C and mu, the both contrasts give the nice estimation in this setting, in this data setting. However, in the case of sigma 2, you will find that the new contrast gives much more accurate results compared with the local Gaussian contrast. This is actually comes from our step size condition is weaker than the step size condition required for the local Gaussian context. So for instance, if we try to make the time steps goes to 0, this is a root mean square error of the sigma 2 estimates. You will see the dramatic decreasing of the root mean square error in the estimation of sigma 2 in the new contrast compared with the local Gaussian contrast. Then finally, we will see the example of low frequency partial observations. We will consider the SIR model. So this is 3-dimensional elliptic diffusion. So we will do the Bayesian inference to estimate the parameter theta. And now the observations are real data of the number of infected people. And we assume there's additive Gaussian noise in observations. And under this setting, we apply standard Hamiltonian Monte Carlo to sample from the posterior. And of course, you can use another Monte Carlo methods rather than standard HNC. And also, I would like to emphasize that in this numerical experiment, it is only required to simulate the diffusion processes. So now we compare them both Euler-Mariam scheme discretization and our sampling schemes. So the first experiments, you will see the posterior distributions. They are calculated from the Euler-Mariam scheme data augmentation. Now the time step between the observations is fixed with 1. They're not small enough. So we need to impute the intermediate values with the sampling scheme. And you will see the two plots. The black one is the tracked quantities computed by the data augmentation with Euler-Mariam scheme with the 1,000. So many imputing intermediate values between the observations. And you will also see the blue plots. This is calculated by the Euler-Mariam scheme with the 20 intermediate points. And you will see the visible differences between black and blue plots. This is actually the bias between black and blue. So in the case of black, we almost eliminate the bias by setting the so many number of imputation. However, in the case of blue, the 20 imputation is not enough to eliminate the bias. So you will see the visible differences between the blue and black plots. So this is the case of Euler-Mariam scheme. However, in the case of some second order sampling scheme, so the orange plot is the posterior estimates using the proposed sampling scheme with the 20 data augmentation between the observations. And you will see there's no, the orange plots capture the black one very well in this case, even with the 20 data augmentation. And please note that the sampling efficiency of the MCMC is the same for both Euler-Mariam and proposed sampling scheme. So only difference is that this bias appeared from the data augmentation. So yes, so we reached to the conclusion. So firstly, we propose the sampling schemes for elliptic and hypo-elliptic SDEs. And those schemes are very useful in the context of the computational MCMC, where the only sampling is required to do some Bayesian inference. And secondly, we obtained some closed form transition density approximation that has a better accuracy in the distribution sense compared with the classical Gaussian distribution. And this attempt is novel in the hypo-elliptic setting. And thirdly, for the MLE based upon the transition density approximation, the CLT holds with the weaker condition for the step size. And this setting, this assumption is actually the weakest condition in literature under the hypo-elliptic setting. And finally, the sampling scheme gives much accurate data augmentation results with a smaller bias of m squared, m to the minus, m to the minus 2, compared with the Euler-Mariam scheme in Bayesian data augmentation. So, yeah, this is differences, and thank you very much for your paying attention.
Thank you so much for your talk. So I guess we can stop recording now. Stop recording. Yes.